Okay, so what I want to do today is I want to talk a little bit more about contraction maps. I want to talk a little bit more about some real analysis preliminaries. It's nice that most of you have seen real analysis. As real analysis is not a prerequisite for this course, I'm going to go a little bit fast on the real analysis. I want to do just enough so that we have the right notation so we can handle problems along these lines, and that if you then want to do more, you know exactly where to look. But I'm not going to require any real analysis for this. So what did we finish with last time? Last time we were looking at contraction maps, and we showed that if you have a contraction map, you have at most one fixed point. But what we didn't show is that a fixed point must exist. And so what I need to do now is review a little bit of the basics of notation, of some useful facts from real analysis. Okay, so let's see. I think we lost the swiveling. Right, so let me see if I can get the swivel to work. All right. So basics from real analysis. So the first is we say xn converges to x as n goes to infinity if the distance from xn to x goes to 0. This is the most informal way of writing down what we mean by some kind of limit process. And I'm being extremely vague about what I mean by the distance here. Okay. What's the first fact you would love to know about limits?
How quick?
One is how quick, but there's more general thing than you would like to know before how quickly you approach a limit.
Whether it's pointwise or uniform?
Okay, so that's types of convergence. That's similar to how quick.
From which direction it converges?
More basic than that.
Whether it does.
I'm sorry?
Whether it does.
Whether it does.
Do you ever actually reach the point?
So there's that, but there's more basic. If I tell you a sequence has a limit, this is very similar to what we just proved for contraction maps.
What's the limit?
Is it unique? Right? Very first thing, is the limit unique? Once you know it's unique, then you can start asking all these other questions. Where is it? How quickly do I approach it? Am I ever actually equal to the limit? So the first question, it is unique. As an exercise, you should be able to prove that it's unique. Here's a rough proof. Imagine not. Imagine you approach the point x and you approach the point y. Well, then eventually, I've got to be very close to x. And eventually, I have to be very close to y. And what I'm going to do is I'm going to say, well, xn minus x has to go to 0. Eventually, it's going to be less than epsilon. So I could draw like an epsilon ball over here. I could draw an epsilon ball over here. And I can choose epsilon to be less than x minus y over 4. X minus y over 4, this is not the smallest thing I need to do. If I did strictly less than x minus y over 2, I would probably be fine. The balls would just barely touch. I never like having delicate arguments where I have to worry about am I just barely making it. Always put in a little fudge factor if you can afford it. We did this when we were talking about the programming constraints. Put in a little fudge factor. All right? So in something like this, if we were approaching x and we're approaching y, then eventually we've got to be with an epsilon of x. Eventually we've got to be with an epsilon of y. We cannot be simultaneously with an epsilon of both if epsilon is sufficiently small. So this leads to the more rigorous definition. For all epsilon greater than 0, there exists an n such that for all n greater than or equal to n, xn minus x is less than epsilon. That's what it means for x to be the limit of the sequence xn. And the limit is unique. How many of you have seen the Cauchy criteria? How many of you have taken real analysis but not seen the Cauchy criteria? Okay, good. Just making sure that the two sets are still equal. So the Cauchy criteria is a great way to show that limits exist. If for all epsilon greater than 0, there exists an n such that for all nm greater than n, we have xn minus xm is less than epsilon, then the sequence converges. Right? This is a wonderful result. It's a nice condition to check. And what it's basically saying is that from some point onward, the terms in the sequence are very close to each other, as close as you want them to be. And that's going to imply the sequence exists and the sequence has a limit. What would you love to know, though? All right, so it seems like we've lost this riddling. All right, what would you like to know? Yes. What the limit is. And so the Cauchy criterion does not directly give you what that limit would be. Okay? So this is unfortunate. In many situations, we are actually able to extract from the Cauchy criterion a limit. Has anybody seen the telescoping method to get the limit? So telescoping series. So this is an extremely common technique in mathematics. When you have a series that you want to add, if you group terms intelligently, it's often very easy. This is a fancy way of writing what? This is a fancy way of writing x1. Now if I go plus x2 minus x1, this is a fancy way of writing x2 plus dot 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 plus xn let's do xn minus xn minus 1. So this is a fancy way of writing xn. What do we know about these terms over here? Yes? They go closer and closer to 0. So is that enough to force this sum to converge? So if I have a sum of terms that are going to 0, will that force the sum to converge? No. Because you've got to be very careful. Just because the terms are tending to 0 does not mean the sum converges. So danger. 1 plus 1/2 plus 1/3 plus 1/4. This diverges. So just because the terms are individually going to 0 does not mean that the sum must converge. So we've got to be a little bit more careful than that. But the hope is that if these are going to 0 sufficiently fast, this whole thing will converge. So there's a couple of key results we need. So let an be a sequence of non-negative numbers. Assume the sum n goes from 0 to infinity of an is less than infinity, then the sum converges. This is a really nice property. Okay? Out of curiosity, how many of you have seen this property? If you have a sum of non-negative numbers that's bounded, the sum must converge. Okay. So let's try to informally see why that's the case. So I start off, here's a 0, and I start adding things. I go higher and higher and higher and higher up. Well, because my sum is bounded, I know there's a certain value I will never go higher than. It's bounded by something. The question is, what's the lowest I can put that? If I look at the partial sums, if I sum up to the first term, 2 terms, 3 terms, 4 terms, 5 terms, those partial sums are strictly non-decreasing. I've got to be careful. Non-decreasing is not the same as increasing. Right? It's possible that some of these numbers could be 0. And so as I sum more and more terms, my partial sums can never go down. They can only go up. And they're bounded from above. So this is one of the properties we assume about the real numbers. When we have sequences like this, they will converge. And so if we keep adding higher and higher and higher and higher, we're never going to overshoot something. Or if we overshoot something, we overshoot it from that point onward. So I'm not going to go into too much detail here. This is just a reasonable result from real analysis that is useful for problems like this. If I have a sequence of non-negative numbers and I keep adding more and more terms, it will converge to something. Okay? Does anybody know the most important series in terms of convergence? What's the key one? What's the one we need more than anything else? I'm sorry?
1 over n squared.
Not 1 over n squared. 1 over n squared is a nice one, but it doesn't really occur that often in problems we care about. Anybody know what the most important series is? Geometric series. The geometric series is the most important one. How many of you have seen a proof or remember, better yet, how many of you remember a proof of the geometric series formula? You know, right now, if I say close your books, I'm going to give you a piece of paper, I want you to prove the geometric series formula. Okay, not that many hands are up. So this is one of the most important series in all of mathematics. And so it's going to be crucial in what comes. So let's talk a little bit about the geometric series. So an is going to be ar to the n. And what we'll let Sn be is a0 plus a1 plus an. It's the sum of the first n terms. Frequently, we do the special case when a equals 1. It's not that much harder to do the general case. So we would have Sn is a plus ar plus ar to the n. If we multiply by r, we get rsn. R times a is ar plus dot 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 plus ar to the n plus ar to the n plus 1. And so when we look at these, if we subtract, we kill everything in the middle. And we're left with 1 minus r times Sn is equal to a minus ar to the n plus 1. So we get Sn is a minus ar to the n plus 1 over 1 minus r is a over 1 minus r minus a over 1 minus r times r to the n plus 1. What's particularly nice about this is you can see what's happening as n goes to infinity. As n goes to infinity, it wants to converge to this. What could prevent it from converging to this? Well, what could prevent it is that this term over here could be exploding. So in order for this not to explode, if the absolute value of r is less than 1, then this term will tend to 0. It'll tend to 0 very fast, and it'll converge to a over 1 minus r. So if the absolute value of r is less than 1, then the limit as n goes to infinity of Sn is equal to a over 1 minus r. If you've seen proofs of things like the ratio test or the root test, what's really lurking in the background of all of these is the geometric series formula. One of the most basic tests we have for whether or not a series converges or diverges is the comparison test. And there, the 1 over n squared that was suggested, the 1 over n, the geometric series, these all come into play as really good examples of sequences whose behavior we know. And then the comparison test says, well, if I have a sum that converges, and I'm smaller term by term than the sum that converges, I must converge. If I have a sum that is divergent, and I'm larger term by term, I must diverge. Of all the tests, how many of you remember these tests? The comparison test, the series, the ratio test, the root test. Which is your favorite test to use? Ratio test. Why do you like the ratio test more than the comparison test? But you are comparing it to another series.
Well, you are.
It's in the background. What's nice about the ratio and the root tests? Now, I don't mean this in a derogatory way, but there's essentially no thinking required. Right? The ratio test and the root test is just plug in, crank through the algebra, and you get a ratio less than 1. If yes, it converges. Is it greater than 1? It diverges. You just crank through and you do the algebra. For the comparison test, what's the difficulty in doing the comparison test? Related to that, what makes the comparison test hard to use? Yeah, you have to find what to compare to. You have to think. Right? This is very similar to factoring quadratics. If your life depended on it, could you factor a quadratic? Yes. What would you use to factor quadratic? Quadratic formula. But a lot of times you can just look at the quadratic and you can see what the roots are going to be, and you can bypass the quadratic formula. And if you can see the answer to a problem, by all means use it. There's no need to do the more painful, tedious calculations. But it's nice to know that if you have to, you have a fallback. The quadratic formula will go through and give you all the details. Okay? So in terms of what's going on in the basic theory, I don't know how much of this was emphasized in your classes. The comparison test is the most important. It's the most useful. What really is happening is you're comparing to a geometric series, and the ratio test, the root test, they're trying to find the right one for you in the background. And that's why things are working. It all comes down to the geometric series. There are other ways of proving the geometric series formula. If there's time later in the semester as we get into game theory, there's a nice proof of this involving a game of hoops between two basketball players. And it illustrates one of the most important principles in mathematics. I'm going to skip that for now and just use the geometric series as given. So for us, the critical thing is a geometric series where the exponents are, where the ratio is less than a half. Why is this useful? Let's go back to our telescoping sum. So we have xn was x0 plus x1 minus x0 plus xn minus x0. What I want to do today is I want to focus on a couple of specific cases and do the calculations in these specific cases, and then just remark, hey, we can generalize all of this. We'll place the absolute value with the distance function and look at what we have. So if you haven't seen real analysis, that's fine. Just think of things with the normal absolute value. If you have seen real analysis, if you've seen normed vector spaces and metric spaces and all that stuff, you can just put that in the other framework. Okay, so I'm trying to have the lecture function at both levels, so if you've seen the additional stuff, you just add a few extra words at the end. But if not, just focus on a specific example. I can write this as x naught plus the sum, k goes from 1 to n, of xk minus xk minus 1. And now we want to understand what's going on here. So now, imagine xk minus xk minus 1 in absolute value is less than equal to c times xk minus 1 minus xk minus 2 for sum c strictly less than 1. So what I'm saying is the distance between two terms, the size of that is less than equal to c times the distance between the two previous. And that c is not allowed to depend on k. It's some universal constant strictly less than 1. Have we seen anything like this before? Where have we seen this? Contraction maps. So when we're doing contraction maps, if we let xk be what happens when you apply fk times to our initial value, this is exactly what a contraction map says, that where you are is closer after iterating than where you were before. If you take 2 points x and y, then f of x minus f of y is smaller than x minus y. How much smaller? Smaller at least by a factor of c. So this situation is exactly what we need for the contraction map study. I'm just isolating it out right now as a special case. Imagine we have a sequence where this holds. So this does hold for contraction maps. With f of xk equal to xk. And so we start off with some point x naught, and we just iterate. So everything I'm saying here will apply immediately to our contraction maps. Okay? What do you want to say about this sum? So what should be true about this sum? It converges. Right? Why should it converge? So that's a reason why it should converge, but it's not enough that it's getting smaller, right? You need to be a little bit more vehement than smaller.
C is less than 1 by what you just erased.
Okay. You're close, but you need to be a little bit stronger than just C is less than 1. So what happens is we keep iterating this. So we want to look at, we know xk minus 1 is less than or equal to C xk minus 1 minus xk minus 2.
Compare it to the geometric series.
So compare to a geometric series. Okay?
C to the n goes to 0.
C to the n goes to 0. So this is the lather, rinse, repeat stage of mathematics. Right? Once you have something like this, you keep using it again and again and again. So this will then be less than or equal to C squared xk minus 2 minus xk minus 3. And then this will be less than or equal to C cubed xk minus 3 minus xk minus 4. And how far down do we go? Don't worry about the power of C. How far down do we go? Where do we stop? x1 minus x naught. I always have trouble in problems like this and trying to figure out what is the exponent of C as I do this. What I always do is the following. C to the first k minus 1, 1 plus k minus 1 is k. 2 plus k minus 2 is k. 3 plus k minus 3 is k. The exponents have to sum. The exponent in the superscript sums to k. So if this is going down to 1, what's the power of C? K minus 1.
The right down there, the contraction maps, is that f of x k equals xk? Is that saying that xk is the fixed point, or are you trying to give a definition for x?
Oh, sorry. Thank you. This should be fx k minus 1. Thank you. Thank you. Sorry. It's mapping us to the next term. So for us, f of xk minus 1 is xk, the next term. Thank you. So we're just mapping all the way down. So now that we have this, not only are the terms going to 0, but they're going to 0 geometrically. They're going to 0 exponentially fast. Think of C as 1/2. Then the different terms are 1/2, 1/4, 1/8, 1/16, 1/32. Even if C is close to 1, 99 out of 100, it'll just take longer, but you're still going to have things getting closer and closer to 0 fast. So now, when we look at xn is x naught plus the sum, k goes from 1 to n of xk minus xk minus 1. This sum, if I replace this with absolute values, it's going to be bounded. So replace with absolute values, bounded. Okay? So now if I replace this with absolute values, it's bounded. Great. But that's not exactly the sequence we have. So now I have a new sequence. But in terms of how large my new sequence could be, it's got to be somewhere between the sum of this with absolute values and the sum of this with absolute values with a negative sign over here. I've got a region like that. And now standard arguments from real analysis will show that this will converge. Because essentially all I can have now is I can have additional cancellation. These terms are going to 0 fast. If you look at the total sum of their contributions from any point onward, it's going to be less than epsilon. So this is another way of looking at it. If I take the sum up to n, and then I go from n plus 1 to big N, and I ask, how much is that? If I choose little n sufficiently large, I can make that contribution as small as I want because it's a geometric series, because I'm getting powers of c to the n. So as c is less than 1, we win as c to the n goes to 0 fast. Okay. So I'm trying to give just enough of a flavor of the details as to how you make these calculations rigorous. All right? So if you want, just really explicitly, going back and seeing how we would do the calculation here, for example, right over here, f of x k minus 1 is xk. xm minus xn, I guess m comes early in the alphabet, so I guess do xn minus xm. This is going to be xn minus 1 plus xn minus 1 minus xn minus 2 plus xm plus 1 minus xm. So this would be a sum. K goes from m plus 1 to n of xk minus xk minus 1. And I have absolute values on the outside. So this is how far apart xn and xm are. Well, xn minus xm, this would be less than or equal to, I bring the absolute values inside. And I would have a sum, k goes from m plus 1 to n of xk minus xk minus 1. I can bound this with the geometric series formula. And this is going to be less than or equal to the sum, k goes from m plus 1 to infinity. Am I allowed to extend the sum to infinity? Yes. That could make it larger. But if I can show that this is bounded and small, if I extend it up to infinity, that's fine. So now I'll have c, and we said it's to 1 power less than the index. So I'd have it c to the k minus 1 times x1 minus x0. And now I have this sum over c. And so I'm going to basically get, by the infinite geometric series formula, this will be c to the m x1 minus x0 over 1 minus c. And what is this going to go to as m goes to infinity? It'll go to 0. So the Cauchy criterion is satisfied. So Cauchy criteria is satisfied. Explicitly, you give me an epsilon, and I can choose a big N such that as long as m and n are greater than big N, the difference between them is less than epsilon. And I can even explicitly figure out what I need to do. You give me an epsilon, and I can play the game, and I can solve for little m. I can solve for big N, for how far down the line I have to go to guarantee that I'm sufficiently close. So the Cauchy criterion is a very powerful way of telling when things converge. Since the whole point of what we're doing now is trying to find fixed points, the idea of trying to find when things converge and what they converge to is quite useful. Okay? All right, so there's a lot of good things we can take from this. The first is that this sequence does converge. The second is we have a nice way of calculating how close we are. And we can bound how close we are after k iterations. So what do you think is going to make us converge faster? The closer c is to 0, the faster you converge. Whenever you have a mathematical statement, play games with it. Choose values of the parameters. What's the friendliest value of c I could give you? I could give you c equals 0. So I want to map a space S to itself. And I know no matter what 2 points you take, x and y, well, OK, if I take c equals 0, this is a little bit extreme. Right? What happens? Everything is mapped to 1 point immediately, including the origin. Sometimes when they do fixed points, they want it to be strictly less than c times x minus y. And if they do strictly less than c times x minus y, it actually excludes the case of the trivial map. The reason you want to do this is because sometimes when you have a case that is so trivial like this, it just makes some of the statements a little bit painful to write down. My calculus book freshman year actually said that when we were looking at vector spaces, sometimes the empty set causes trouble in how you state theorems. Is the empty set a vector space? Do you have to have a 0 element in a vector space?
Well, but those are different questions. Oh,
Well, depending on how you define it, technically you only want a zero element such that 0 plus v equals v plus 0 equals v for all v in the vector space. If your vector space is empty, do you ever need a v to come in? No. This is not why you signed up to take upper level math classes, to split hairs on whether or not the empty set is a vector space, right? Is this a vector space you would want to study? No. And so a lot of times it's just tacitly excluded. Let's not worry about something like that. In any problem of interest, there will be objects. Things that are objectless are not too interesting to study. However, in what we're doing here, are there situations where there are sometimes no feasible solutions? So all of a sudden now we do have to worry about maybe considering the empty set, right? Because all of a sudden now we don't know a priori that there will be something present. So these technical issues, they are worth thinking about. How do you want to define things? If you define a contraction as it's strictly less than c times x minus y, that does eliminate the map that sends everything to 0. Okay? We are not going to really study the map that sends everything to 0 in this class. Okay? This gives us a proof that if we have a contraction map, or more generally, if we have a sequence where the difference between adjacent terms is going to 0 exponentially fast, then this sum converges. Then the original sequence xn converges. And in fact, here is a way to calculate what it converges to. This is the part that really needs to be emphasized. All right? It is an explicit formula to calculate what things converge to. You just keep adding terms like this, and this will converge. Okay? This is xn. So we've now shown that the sequence xn converges. All right. So I will isolate this out as a theorem. F from S to S is a contraction with some c less than 1. Then, one of you have seen this notation? This means there exists a unique. There is a unique fixed point. And what we can do is we can let xk be f of xk minus 1 with x1 equal f of x naught. X naught is arbitrary. Okay? What do we know about the sequence now, xk? What do we know about the sequence?
It goes to 0. Or it
Not that it doesn't necessarily go to 0.
converges.
It converges. This converges. The sequence xk minus 1, that converges to 0. So these different sums will converge. What do you think it converges to?
Fixed point.
Converges to a fixed point. So how does this imply that x is the fixed point?
How does what apply?
We know that xk converges to something. Let's call it x. I mean, what would we call it? Y? I mean, we'll call it x. It seems reasonable that x is the candidate for the fixed point. We need to prove that x is the fixed point.
Well, because we haven't specified which index k, so all k goes to.
Okay, so we know xk goes to x. We also know xk plus 1 goes to x. But what is xk plus 1?
It's like the next item in the sequence.
It's f of xk. Okay, so if we look at what we have the limit as k goes to infinity of f of xk equals x. What do we want to do? I would say it's not apply f to both sides.
Last class you said you can find a fixed point by keep applying f over and over again.
Mm-hmm.
And you get a fixed point. So if you use that method here, keep applying x, x1, x2, x3, all the way through the sequence to eventually arrive at a fixed point. And it's a contraction map, the other is a fixed point. So it would be x.
You're close. What do we want to do? We have the limit of f of xk equals x. Yes?
You take the limit in.
You put on your physics hat, your economics hat, you move the limit inside the function. And say that this is the same as f of the limit as k goes to infinity of xk. Are we allowed to do this? Yes, by continuity. So xk is converging to something, f is continuous. So we can now evaluate f at the limit of xk. Well, what is the limit of xk? X. And there's the punchline. And now we get f of x equals x. So this gives us a constructive way to find the fixed point. This is one of my favorite methods in all of mathematics. Choose a point. Doesn't matter. Choose a point. Keep applying f. Eventually you will hit the fixed point. We can even quantify how quickly we are reaching the fixed point. This is constructive. Okay?
What does eventually mean?
Well, eventually means a time infinity. But we can quantify how close we are at any finite stage. And so as time passes, you want it to be within a certain threshold of what the fixed point is, we can get there. And this is very constructive. What I thought I would do, we've got a few minutes left in class today, I thought I would do differential equations for just one day on Wednesday. Friday will be no class so that you will have time to work on the exam. By all means, I encourage you to have the exam done before Friday, but I will give you Friday for the exam. The policy is you're supposed to have a class off whenever there is an exam outside of class to balance things. What I thought I would do is I would end today with a situation, it's a game theory problem. There is, in some sense, a sort of a fixed point. We'll say there's a winning strategy, but it's a non-constructive winning strategy. And so I will give enormous extra credit to anybody who will give me the winning strategy so I can defeat my 7-year-old son. Okay? I am not a proud man. Okay? If you can help me beat Cameron. The other thing is Kayla and I did put down a hint to one of the problems on the exam somewhere in the Williamstown environs. So there's now a public hint. Good luck finding it. But it is public, and it's somewhere in Williams or a Williams-affiliated institution. I think there are better ways to use your time, but you know, it is there. There were some comments about why I was doing what I was doing, but they did let me do it. All right. So here is the dot game. So m and n are positive integers. Consider m by n board of dots. 1, 2, 3, 4, 5. No. Actually, I think, no. Just to be safe, the way Cameron and I are playing, we put the white dot there. And again, I hate doing this on the blackboard because it's not clear what is the white dot, what is the black dot. So we'll say, we'll do filled and unfilled. So there's one unfilled dot. Every other dot is filled. On your turn, you choose a dot, kill all below and to the right. Okay? So for instance, if I choose this one, I would kill off all of these dots. I kill off everything below and to the right. Okay? Is it whom or whoever? Whomever? It's who?
Is it the subject?
Whomever takes the unfilled dot.
Whoever.
Whoever? Okay. There's advantages to teaching at a liberal arts college. Whoever takes the unfilled dot loses. You do not want to take the unfilled dot. I haven't written it, but obviously you alternate moves. Do you want to go first or second?
No, first.
So the question is, does one of the players have a winning strategy? One of the reasons why we're doing fixed point theorems, how many of you are econ majors or considering an econ major? Not quite half the class, but a sizable amount. One of the big things in economics is game theory. Game theory is not going to be taught at Williams this year, probably not next year. So this is how many of you have taken a game theory class? Okay, so since a lot of people, this is a useful subject, but it's not going to be taught, I do want to put a little bit of game theory into operations research. This is an outstanding topic for operations research. If you've ever seen the movie War Games, this is a nice example of game theory. All right, so over here I have two players. And one of the reasons people care so much about fixed point theorems is you can use these to find winning strategies for games, but not always constructively. So the question is, does this game have a winning strategy? And if so, for which player? For the player who goes first or the player who goes second? Yes?
Well, if the person who goes first chooses, say, the top,
This one?
the point directly to the right of the unfilled point, then the second player has a winning strategy, right?
Okay, if they choose this one, then
Everything's wiped out, and then the second.
wait, no. If they choose this one, no. The only thing that's wiped out is this column. You kill everything below and to the right. So if you choose,
Just the dot right to the right of the unfilled one.
oh, this one?
Yes.
Okay, so if you choose this one, then you're left with this row over here,
And then the second person.
and then the second person will choose here, and the second person will win. So bad idea to choose this dot if you go first. Okay, so if you're looking for a losing strategy, so all you have to do is multiply by -1 and you've got it. So email me for extra credit. Yes. Cameron would be very appreciative of that. So I will try that on Cameron and see how happy he is tonight.
What if the first player chooses the one diagonally down from the unfilled dot?
Right here?
One up to the left.
Right here?
Choose that one.
Okay, so if you choose that one, now I've got a number of things in this row and this column.
So the second player.
And the analysis is now going to become involved. If you can tell me how to win in that situation, and if it depends on how many here and here, I'd love to know that. I have not thought about that. For those of you who think that this is an unfair advantage, if Cameron wanted to, he could be talking to his second grade class. He's got more recess time than I do. Okay? I'll take one more suggestion, and in the interest of time, I'll say, do you agree that somebody has a winning strategy for this configuration?
No.
No?
Well, for m and n both equal to 1, the first player loses instantly. For m and n equal to 1 and 2.
All right, so let's say Let's say m and n are greater than or equal to 2. Or if you want, we'll even make it greater than or equal to 3 to make the game big.
It ends up mattering whether or not it's like even or odd.
So there's a lot of things where it could depend on parity. But do you agree that if I give you a board that's, m and n of at least 3, that one of the two players should have a winning strategy? Because somebody's got to end up getting that dot. Here is the one-line elegant proof that player A, whoever goes first, has the winning strategy. Okay? Imagine B has a winning strategy. Okay? So that means when A moves, B has a winning way to respond. A chooses the bottom right corner. Now B has a winning strategy. Where should B go? We're assuming B has a winning strategy. Where should B go? Wherever his winning strategy is, wherever her winning strategy is, that's where B goes. I don't know where it is. Let's say it's over here. And now by going there, B wins the game. What should A do on A's first move? Just go where B would have gone. Yes?
Who's to say that B's winning strategy wasn't to go to A?
Can't. Because no matter where A goes on the first turn, that piece is gone. Good fear. A has a winning strategy. What's the problem about A's winning strategy?
Conditional on B.
It's, well, conditional is not necessarily the right word because B does not have a winning strategy. It depends on figuring out what the winning strategy would be from a different configuration, which we don't know, without doing exhaustive searching. This is the best example I know of to just really illustrate the difference between constructive and non-constructive. I've lost to a 7-year-old, okay? Yes, he has the advantage of having done a lot of math with me since childhood, more than I did at his age, but I'm still losing to a 7-year-old, right? This cannot be allowed to stand, right? I know that I have a winning strategy if Kim lets me go first. That makes it even worse when he beats me, right? So I'm trying to really drive home the point of the difference between constructive and non-constructive. I have a proof that A has a winning strategy. I do not know how to reach that winning strategy. So if you want extra credit for this class, give me a winning strategy as a function of m and n. Tell me where I should go if I'm going first. Okay? All right, so we will do differential equations in one day.